to my presentation on graph neural networks. Today I'll be covering what a graph neural network is and some applications in the biomedical field. But before I do all that, I'll be explaining some fundamental concepts related to artificial neural networks. First off, what is an artificial neural network? So an artificial neural network is an attempt to use computer systems to simulate the connections in the brain that allow us to process information. And to do this, data is sent into the network through this input layer. And as it interacts with these layers of neurons found in the hidden layers, it will undergo a series of transformations and linear combinations before the data reaches this final output layer. And this is where the computer will make a prediction based on probability. So this is an example taken from a great YouTube video that explains the basic concepts of artificial neural networks that I will link in the description below. And what this example is trying to do is it's trying to take this image and classify it into three categories. So it's trying to identify if this image is a circle, a triangle, or a square. And to do this, the image will initially be broken down into individual pixels and represented as a column vector. And what that means is that each individual pixel will be an X value that is inputted into the network. And as these X values interact with these hidden layers, it will be transformed until it reaches this final output layer where the computer will identify what shape it is. And as we can see that this network identifies this image as a circle with a probability of 0.9. And this probability value is usually a number that ranges between 0 and 1, where the closer it is to 1, the higher the confidence that the image is correctly identified by this network. Therefore, as this image has a value of probability of 0.9, we can kind of understand that the model is well trained and is able to classify circles. And now you might be wondering, how exactly did the network come up with this prediction? What really was going on in the hidden layers that allowed it to come up with this result? And to do that, you have to understand what are weights and biases. So weights, which are these kind of connections between different neurons, are an indication of how strong the connection is between neurons. And if we think of an actual brain where the stronger the connection is, the increased firing of action potential, this is the same thing in an artificial neural network where the stronger the connection is, the higher the weight value is. On the other hand, there are these biases, which are values we associate with each neuron, and they indicate how important a neuron is. And if we think of a neural pathway in the brain where not every neuron plays the same role in the pathway, and some neurons might be more significant, a bias is trying to take that into account in an artificial neural network. And finally, as this data kind of travels through these layers of neurons, every time in every layer, you will add these weights and biases and kind of find a linear combination of these values, which will be inputted into the next layer of the neural network. And this will keep going forward with each layer until it reaches the final output layer. And that's kind of how we're able to come up with this prediction. But now you might still be wondering, how do we actually determine these values for the weights and biases? How do we train the model to come up with these values? We can train an artificial neural network in almost the exact same way we train a biological neural network. So there was this study in 2015 conducted by the University of California that claimed pigeons could diagnose cancerous tumors in the breast with about 99% accuracy, which is about the same as a doctor's. And that sounds almost shocking. How can a pigeon do that? But if we look at a pigeon's brain as an artificial neural network, it's really not as crazy as it sounds. So an artificial neural network is actually much more simple than a human brain or a pigeon's brain. But what makes it so powerful is the way that we train it to recognize specific patterns. And this is exactly what was done to the pigeons in this study. The pigeon didn't suddenly develop the ability to understand what cancer was and to know what they were exactly doing, but what scientists and researchers did was they were able to train these pigeons to recognize specific patterns and kind of learn what would give them rewards. So that's the first step of how we train a biological neural network. We have to be able to give it reward. And that just means that every time the pigeon got a right answer, it was given a treat. And the second step is that we want to ensure that the pigeon's actually learning and not just merely memorizing pictures, but it's actually learning to recognize patterns. And to do this, researchers had to constantly shuffle the order of the images as well as introduce new images into the set that the pigeon had never seen before. And that was a great way of evaluating if the pigeon was actually learning these patterns. So we can take this exact same approach in how we train an artificial neural network. How do we reward a computer system or an artificial neural network? To do this, we use something called the cost function. If we looked at the previous example of trying to classify an image as a circle, a triangle, or a square, we'll notice that the network accurately classified the image as a circle with a probability value of 0.9. However, this probability value isn't actually what we would expect, because when we looked at the image, we knew with 100% certainty that the image was a circle. So the actual output should have been a 1 for the circle and 0 for the triangle or the square. So this difference between the actual output and the predicted output by the network is called the error. And this error can be used to calculate cost function. And the whole goal of training an artificial neural network is we want to minimize the cost function because that means the actual output and the predicted output are almost the same. And to train this model, what we'll initially do is when we create an artificial neural network, we'll set every weight and every bias to whatever value we want. It doesn't matter at that point. But every time we input information into the neural network, we'll get a predicted output, and we'll use that to calculate the cost function. By taking the partial derivatives or the gradient of the cost function, we'll be able to undergo this process called gradient descent, which is when we want to move all the weights and biases in a way that will move the gradient in a direction that minimizes the cost function. So a way to visualize that is we look at this graph on the left. On the y-axis is the cost function, and on the x-axis is the values of the weights and biases. So when we had initially set all the values, all the weights and biases in the network to whatever we wanted, there was this high cost function. However, every time we inputted data into the network and calculated the cost function, as well as the partial derivatives, we were able to take this step towards the minimum cost. So every time we did this, we kept repeating this process over and over again with new data and kept taking these steps that would minimize the cost function until we reached close to the minimum. And that's where a good artificial neural network will want to situate themselves. And the second point I mentioned was for training a biological neural network is we want to ensure that the network is actually learning and not just memorizing information. And to do this, an artificial neural networks use this concept of the training versus the testing set. So when we have all this information that's going to be inputted into our neural network, most of the data will be used to train the model and to kind of minimize that cost function. However, there will be a small set that's called the testing set, which is information that the network has never seen before. However, after the model is well trained, we will introduce this testing set, and it is a way of evaluating if our model is actually accurate. Has our model learned to recognize these patterns that it can use on information it's never seen before? Therefore, if the testing set outputs good values that still kind of minimize that cost function, it means our model is accurate and can be used again to track our data. A popular type of artificial neural network used for image analysis is called a convolutional neural network. Unlike the previous artificial neural network we saw that broke an image into individual pixels and analyzed each pixel individually, a convolutional neural network will look at whole sections of an image at a time, or look at multiple pixels at once, and try and extract key features using something called convolutional filters. So we look at the image on the top left of this convolutional layer. What occurs is that there are these layers of neurons that will look at a same input from a unique lens. And this lens could be just the edges of an image or just the colors of an image. And it will use these qualities to build feature maps as seen on the bottom right. And in the next level, after these feature maps have been created, is that we will pool these feature maps together and eventually match them to known templates in order to identify what this input image is. And a great example of how this is actually being used at the Deepmind lab was using a convolutional neural network to diagnose brain tumors. And how this occurred was an image of a brain tumor was inputted into a convolutional neural network. And using these convolutional filters that would look at specific sections of the brain tumor and try and identify either the color or the texture and build these feature maps, we were able to then match them to known information or known templates about if these features might make a brain tumor more cancerous. And from there, we were able to predict if this brain tumor was cancerous or not. I want to briefly go over in a little bit more detail the difference between artificial neural networks and convolutional neural networks, and why convolutional neural networks are so much better at image analysis. And a great way to do this is if we look at these two images on the left. So immediately we see that both of these images are representing the number 3. However, if we looked at the exact location of the white pixels in the image, we would notice that they were actually in very different spots. So if we look at the image on the left, the 3 is tilted more so to the right, whereas the 3 on the bottom is more so tilted to the left. So if we looked at purely just the spatial location of these white pixels, these two images would be quite different. But the reason why we recognize these two images both as the letter number 3 is because we see these two distinct loops that are connected. And that's exactly the difference between an artificial neural network and a convolutional neural network. Instead of looking at each pixel individually in relation, and its absolute location, a convolutional neural network is more similar to the way we actually look at images. We will look for key features and how they're related to each other. And what that means is that there's a lot more flexibility when we're looking at an image, and that even if an image is slightly altered or resized, we'll still be able to recognize it. A type of artificial neural network that is commonly used for sequence processing is called a recurrent neural network. Unlike the previous networks that we looked at, where the data could only travel forward, where from the input layer, the information had to keep going forward until it reached the output layer, a recurrent neural network is able to travel both forward and backward through the system, which allows it to possess memory of previous inputs. This is really useful for text and speech processing, because when we read words, we look at each individual letter, but we need to consider what came before in order to change these letters into words. For example, if we looked at the color red and all I told you was that the last letter was D, you wouldn't know what word I was saying. You have to look at what came before. And that's exactly what a recurrent neural network does. A really common use of recurrent neural networks that we're actually using at the Deepmind lab is in order to convert audio text into written text. And how it does this is it will look at an audio file and extract really small slices of audio that may not be even a full letter, it might just be a sound. But by taking into consideration of what came before and what those previous slices were, you're able to build together letters and eventually words in order to convert this audio file into a written transcript. Finally, on to graph neural networks, which have become extremely popular recently due to their increased flexibility and expressive power. To understand what exactly a graph neural network is, we have to first understand what a graph is. And a graph at its core is just a way of modeling relationships. But this is extremely useful because we don't often consider things in isolation. We always want to know how things can influence each other. And that's exactly what a graph does. So a little bit of terminology about how we refer to graphs. So there are these nodes, which are the points or objects themselves, and the connections between these nodes are referred to as edges. And some common applications of graphs in our everyday lives include social networks that are commonly used by business companies, where each node might be a person, and the connections or relationships these people have with each other are the edges. Another example is in chemistry to represent molecules, where each atom might be a node and the chemical bonds are the edges that connect the atoms. And a more exciting application in the neuroscience field is brain connectivity, where regions of interest in the brain are represented by nodes, and the functional similarities between these regions are represented with edges. A graph neural network is different from the neural networks we previously discussed because it's able to take in the input of a graph, often represented as an adjacency matrix. And what an adjacency matrix is a way of representing if there exists a connection between nodes. And how you do that is that all the nodes in a graph are listed along the x and the y axis of the matrix. And if there exists a edge or connection between two nodes, we'll put the value of 1 in the table, and if not, we'll put the value of 0. So if we look at the graph on the left and we see that the node 0 is connected to nodes 1, 2, 3, and 4, if we look at the 0 column or row, we'll see that there's a value of 1 with the nodes 1, 2, 3, 4, and the nodes 1, 2, 3, 4. Now, when we input this adjacency matrix into our graph neural network, there will usually be 3 outputs. And I will go through an explanation or an application of each type of output in the next few slides. But as a brief overview of what these 3 types of outputs are, is that the first one is a node level output. And this output will give you an indication or value related to the nodes. And this is really useful when you want to categorize or classify these nodes. The second type of output is called an edge level output, and this will give you information or value for your edges. And what's especially useful about an edge level output is that it may even create new edges between nodes, which indicates that there's a new relationship between nodes that we didn't even know existed prior. And finally, the last type of output is a graph level output. And this is usually a single value that will relate to the graph as a whole. And this is really useful when you want to generate complete new graphs and want to compare different graphs to each other. The first type of output, as I mentioned previously, is the node level output, which computes values for each node in the graph and is useful for node classification. Now, an exciting application of this technology was released by Google Deepmind at the end of 2020 in this project called AlphaFold 2. So AlphaFold 2 used a graph neural network to predict the 3D structure of proteins based purely on the amino acid sequence. Now, for context, this has been a problem that researchers have been trying to solve for over 50 years with little to no success due to the almost limitless possibilities of amino acid locations in 3D space. So how Google was able to use a graph neural network to solve this problem was that each node would represent an amino acid in the sequence. And they used 2 types of edges, a residue-residue edge, which indicated shared chemical properties or similarities between amino acids, whereas a sequence residue edge indicated a shared evolutionary history between amino acids. So now when this graph was inputted into the graph neural network, the output generated the 3D positions of each amino acid in a 3D space. So it gave you the X, Y, and Z coordinates. Now, this graph neural network is thus considered a node level output because it gave you values for each amino acid or each node. So the next type of output is the edge level, which is used to predict values for each graph edge or a transformed version of it. Now, an application of this technology was released by Stanford in 2018 in this project called Decagon. And what Decagon was trying to do was predict novel side effects between drug and protein interactions. And they did this by building a graph where each node represented a drug or a protein, and the edges represented the already known side effects between these drugs and proteins. Now, by inputting this graph into the graph neural network, the network was able to generate new edges or new connections between nodes that were initially not connected. And what that means was they were able to find new possible side effects based on how similar these different drugs and proteins were. Now, technology was actually highly successful. I believe it was 60% more successful than a lot of the other existing technology. And in one instance, this graph was able to generate 10 novel symptoms that were not recognized by the FDA. However, by cross-referencing other journals, they were able to find that 5 of these side effects have already been discussed in research papers. Now, this just goes to show the potential of this technology and graph neural networks as a whole. The final type of output is the graph level that predicts a single value for an entire graph and is mostly used for classifying graphs or computing similarities between them. An application of this technology was released in a study by the University of Siena at the end of 2020. They wanted to use graph neural networks to generate completely new molecules. How they did this is they used graph to represent molecules where the nodes represented atoms and the edges were the chemical bonds. By inputting this information into a graph neural network, they were able to come up with two different types of outputs. The first one was to generate completely new molecules that had a really similar drug likeness. And the second case was to optimize existing molecules by maybe removing those unwanted side effects while still keeping those desirable properties. And this type of project is a graph-level graph neural network because the final output is a single molecule or a whole graph. Because we are a neuroscience channel, I wanted to end today with an application of graph neural networks in brain analysis. So this study released by Yale University last year used graph neural networks to analyze fMRI images to identify neurological disorders. How they did that was they took a large data set of fMRI images to build functional graphs where nodes represented the regions of interest in the brain and the edges represented the functional connectivity between these areas. And by inputting this graph into a graph neural network, they were able to identify biomarkers and community clusterings in the regions of the brain. And this information could be used to predict neurological disorders. Now, they used this technology on his autism spectrum disorder dataset and were able to find that the results were quite similar to previous neuroimaging analysis technologies. As you can see, graph neural networks have gained a lot of momentum in the past few years. I'm excited to see what else we'll be able to do with this technology, and I hope you learned something new and enjoyed today's video. Make sure to like, subscribe, and comment below.